This is about 1 centimeter, right? And the width, at what frequency can we consider this electrically short? What's the upper frequency you believe we can still assume this is electrically short? 1 centimeter. What about 1 gigahertz? What's the one wavelength of 1 gigahertz? In vacuum? In vacuum, it would be 30 centimeters, right? And in cable, it's probably about 60%, so it's about 20 centimeters. So compared to 20 centimeters, this is 1 centimeter is still electrically short, right? What about 10 gigahertz? Is this still electrically short? What's the wavelength of 10 gigahertz signal? 2 centimeters. This is half wavelength. What it means is this cross section. Okay, when you see you have a cross section, right? Okay, when you see that there's a voltage here, what it means is the voltage from here to here should be the same, right? That's why you have a voltage. Oh, sorry, E field. So E field. The E field from here to here should be the same. So the E field times the radiance will give you a voltage. Okay. But if this is half wavelength long, now what's going to happen? If this is half wavelength long, if this is the E field, you can see that the E field is not constant. Okay. If the E field is not constant, it's time where it changes with time, then you don't have a voltage definition. You don't have a constant voltage definition. You cannot assume that voltage is defined. Okay. So that's why, if that's not true, a lot of PhD students are working on this. If it's not true, okay, to transmit a signal that's 30, let's say 30 gigahertz signal through this, then the circuit model is very complex because you have to consider the cross section. There's a time varying E field on the cross section. But if we assume this is very electrically short, we only need to worry about time varying signal on the line. That's much easier to deal with. Okay, so whenever you break one constraint, then there's a new field. Okay, if you go to graduate school at master degree level, you break some constraints. At PhD level, you break more constraints. Okay, and then you have to do a lot more study because of that. Okay, all right. So as much as possible, we don't like to use wave propagation to study transmission line. We like to use circuit because we understand circuit much easier, much better than a wave. So under these conditions, we can model a transmission line with using capacitor inductors, which is going to be circuit models, like impedance. Okay, capacitor, inductor, impedance, they're circuit models, right? They don't have a dimension, they don't have geometries. Okay, so and this is one example of so-called microstrip. This is a conductor, that's another conductor. This is like a printed circuit board. You have a top trace, and then you send a signal through a top trace. Actually, this is not really a TEM. It's called a pseudo TEM, because to be a TEM wave, remember E and H must be normal to each other. But you cannot make it normal. You can see that this here, that's H field, that's E field. Definitely this is not normal, right? Okay. And over here you can see that that angle cannot be normal. So this is so-called pseudo TEM wave. It's still okay to model this at TEM, but it's more or less TEM, but not exactly. Okay. Okay. As I said, under those conditions, we can model a transmission line with inductance capacitances. Okay, and then if we model loss, we can put a resistor here and then conductor there. Okay, but if we assume it's lossless, then we're going to have inductance capacitors. Okay, so this is the circuit model of transmission line. Okay, with inductance, capacitance, and so on. Okay. And this is a model of transmission line from wave point of view with E and H. Whenever we see E and H, it's a wave. Okay. So I put it here just for completion. I'm going to talk about this. We're going to go right away to circuit. Okay. This is a description of transmission line with circuit parameters and then inductance, capacitance parameters. Okay. So there are two ways to describe transmission line. One is wave, one is circuit. Okay. And assuming, and this is a circuit. How do we derive an equation for this? The way to derive equation is assuming this is the length, this is delta Z, that's the length, times the per unit length inductance. That will give you the total inductance of this piece, right? Okay, and then the delta Z times per unit length capacitance will give you the capacitance of this piece. Okay, then you draw capacitor inductors network to model a transmission line. Okay. Once you've done that, you can use circuit property of inductor and the circuit property of the capacitor to derive so-called wave equation. Okay, because if you take partial derivative of this, okay, and with Z, you can. No, sorry. This is voltage change. Okay, in the voltage change between these 2 points is equal to, and with this formula, the total inductance times current change with time. Right. This is voltage change in space. Okay, between these 2 points. That's a partial change of V times total inductance is equal to the current change in time. That's the property of the inductor, right? It's nothing. And that change is negative because the voltage at this point is higher than voltage at this point, right? Because the voltage is going to drop. There's a voltage drop across this inductor. Okay, this basically describes that voltage drop. Okay. Similarly, if you look at this inductor, there's a current that goes through this inductor. That current is equal to total capacitances times the voltage change across this inductor. Okay, so if you take if you move delta Z to this point, then you're going to have delta V over delta Z, which is the spatial change, is equal to inductance times time change. Okay, so voltage change in space is proportional to time change of the current. Okay, so with this tool, if you combine this tool, you can get the wave equation. Okay, that's how you basically take second derivative of this. That will give you eventually that equation, which is a standard wave equation. We've all seen this in mathematics, right? Once we come to this point, then it's math. You lost all the insight of physics. You don't care about physics anymore, right? It's just math. Okay. This, by the way, it happened that this LV is related to the speed of wave propagation. Okay. So you can have, this is time domain wave equation. This is Laplace domain wave equation. And the wave equation can be solved by making assumption that, and this is the solution, and then you can substitute V into this, and then to find out the positive wave and negative wave parameters and so on. Okay, so that's from here onwards, it's all mathematics. Okay, so I'll go through this very quickly because you've seen wave propagations, wave equations in mathematics, right? Okay, and so I'm going to and then one parameter which is very important, which is called characteristic impedance. Okay, if you take V plus and V over I plus, okay, and then that will give you a constant. You can derive this constant from the wave equation. That constant is L over C, square root of L over C. that is defined as an impedance. And that impedance is called characteristic impedance. Okay, so that impedance actually is not, the unit of this is ohm, but it's not really a resistance because there's no energy loss, right? Remember, resistor is an energy conversion device. It converts electrical energy to other energy, light, heat, motion, and so on. But this impedance is basically just a ratio of these two, but it's not an energy conversion. So, for example, this transmission line probably is a 60 ohm, 50 ohm transmission line. When we see it's a 50 ohm, 60 ohm transmission line, we're basically talking about the ratio of this is 50 ohm or 60 ohm. Okay, but it doesn't mean that there's a 50 ohm resistance that will convert energy from electrical energy to other energy. Okay, it's just a ratio. Okay, that's another concept. That's a characteristic impedance. All the transmission lines will have fixed characteristic impedance. Okay, usually usually the transmission line will have a part number on this, and sometimes it will just write a characteristic impedance value on this cover of the transmission line. I don't see anything on this line. Okay, so from the wave point of view, there's a right going wave and left going wave, right? That's again from you've probably seen this in your math class. Okay. Okay, so this is the transmission line. We're going to talk about this with these per unit length parameters, inductance, capacitance, and the characteristic impedance. Okay, and of course the speed of line, the phase speed of the line. So they're related. Okay, and because it's wave, you have one wave that's a positive going wave, and it's plus or minus here. And then positive going current, and then you also have a negative going wave and negative going current. Okay, so it's happened that the ratio of this is equal to Z0. Okay, and the ratio of the other one is the negative going wave is also equal to Z0, but because of the sign, there's a negative there because the current, one current is going this way, that current is going this way. Okay, that negative sign basically describes the direction of the current. Okay, the total voltage here is equal to the sum of these two. Okay, the total voltage is always equal to the sum of these two. The total current, you can see here, is equal to the difference of the two, assuming the total current is going in this direction, right? Okay, so on the line you can decompose the total current into two components. One is going this way, the other is going this way. You can decompose the total voltage into two voltages. One is a forward going voltage, the other is negative going voltage. So that's how we can model a transmission line with the circuit model, okay, which is much easier to understand than the field model. Okay, so that's circuit model of transmission line. All right, this is a summary of this. Okay, again, Z0. This is pronounced as Z0. Now means 0. Okay, so Z now means Z0. Okay, or Z sub 0. Sometimes you see Z sub 0. Z sub 0 is a function of the structure of and the material property of the line. Once we made the transmission line with some dielectric material inside, then this impedance is fixed. Okay, so, and of course the speed of line is also fixed. All right, and the rest are defined as, for example, this basically tells you how much time it takes for a wave to propagate through this. This is called time of flight, which is basically equal to length of line times divided by the speed of line, right? Okay, that's time. So this L is the length of the line. This is the inverse of the speed of the line. Okay, so that basically, given the speed of the line, given the length of the line, we know how long it takes for a wave to travel from one end to the other end, which is called time of flight. And this is another description way to describe time of flight. Okay, that basically says delay per meter. Sometimes it's used to describe transmission line. Okay, but most of the time we use this to basically to see the time of flight or propagation delay of the transmission line. Okay, and the propagation delay, of course, is related to dielectric material. Okay, this is dielectric material constant. The larger the constant, the slower the wave propagation. Okay, all right. Now, the main part of the course of the lecture, which you need to understand to do your homework, which is reflections. We're not going to talk about general theory of transmission line, because that's you can find books of a few hundred pages book on transmission lines. Okay, and there are a lot of PhD theses on transmission lines. We're going to study transmission line related to digital systems. Okay, so we know this, and we know when wave propagates through the transmission line, okay, there's a positive wave, there's a negative wave, right? Let's use this line here. Okay, so the wave propagates through this. Let me erase this part. And then at this end, it hits a load. Okay, that's a load impedance. All right, on the load, there's a voltage, there's a current, right? That's the total. Okay, so this, by Ohm's law, we have this. That's Ohm's law. But then the voltage is related to, is the sum of two voltages. One is forward going voltage, the other is negative going voltage. And the current is the sum of these two currents. Yes. Any question? Okay. The current at this, right at this point, notice that there's current is a sum of two currents. One is going this way, the other going the other way, right? That's what I replace current with V plus divided by Z naught, and then negative current with V minus divided by Z naught. Then I can get this expression, but if I define a constant which is called reflection coefficient, okay, and which is equal to V minus over V plus. Okay. What this is, if I have an incoming wave, if incoming wave hit this point, okay, there's a reflected wave. And this is a reflected wave. So this is reflected, this is incoming. This ratio basically is a ratio of how much, the percentage of this wave that's been reflected. Just like a water wave, right? When the water wave hit a cliff and then there's a wave that's reflected. This is the ratio. But it happened that if you look at this, if you divide this by V plus, divide the whole thing by V plus, then you're going to get this. 1 plus gamma and 1 minus gamma, which is times C naught. Okay. So, and then from there you can get this reflection coefficient is equal to load impedance minus the line impedance divided by load impedance plus line impedance. And that's a very useful expression, okay? So because that basically tells us if I have impedance here, if I know the line impedance, which is C0, then I can calculate how much wave is going to be reflected if I know the incoming wave, okay? So that's a very important formula there, okay? The reflection coefficient. All right.